August 27th, 2016. A spacecraft called Juno is falling toward Jupiter for the first time, dropping to about 5,000 kilometers above the cloud tops, closer than anything has ever deliberately flown. There is a man on the ground waiting for what it sends back. His name is Scott Bolton, and years earlier he had an instrument built for one purpose, which he can state in 5 words. He wanted to see underneath. Everyone has seen the clouds. People have been staring at those swirling bands through telescopes for 400 years, and every photograph ever taken of Jupiter is a photograph of the same thin outer skin. He wanted what was below it, and everyone already knew, roughly, what was down there. The layers would be neat. The atmosphere would be evenly mixed, the way an atmosphere is supposed to be. And far beneath all of it, at the center, there would be a dense core of heavy elements, the seed the entire planet had supposedly grown around. Every model of how Jupiter formed required that seed to exist. The data comes back. The atmosphere is not evenly mixed. The layers are not neat. And the thing at the center, the one piece every theory depended on, may not be there at all. So let's go down there. The planet is Jupiter. And the problem with Jupiter is the same problem as the eggs. We know its size very precisely. We know its shape very precisely. We know its mass very precisely. What we do not know, what nobody has ever known, is how that mass is arranged on the inside. You could imagine a version of Jupiter with something very heavy sitting in the middle and a light, fluffy region wrapped around it. You could imagine a version where the mass is spread out evenly all the way through. Both of those planets would weigh exactly the same from the outside. Both of them would look identical through a telescope, so somebody had to go and spin it. The spacecraft is called Juno. It launched in 2011, and it arrived at Jupiter in 2016, and since the moment it got there, it has been flying a polar orbit, meaning it does not circle around the equator like most spacecraft do. It comes in over the top of the planet and out underneath it. Every 53 days, it makes one enormous looping pass, dropping down to around 5,000 kilometers above the cloud tops before swinging back out into the dark. The mission's principal investigator is a man named Scott Bolton at the Southwest Research Institute in San Antonio. Bolton is the reason Juno carries an instrument called the Microwave Radiometer 6 microwave antennas that work together as a single instrument, each one tuned to a different wavelength, from about 1 1/3 centimeters out to 51 centimeters. He designed it for one purpose. He wanted something that could look through the clouds. That instrument is going to matter enormously later. Hold on to it. Because the goal of the mission was never really the clouds. Bolton has said it plainly, one of the reasons we study Jupiter is that we want to understand how our solar system formed. Jupiter is thought to have formed first, before any of the other planets, partly because it is the most massive object out there by an overwhelming margin. Every other planet in the solar system could fit inside it. 1,000 Earths could fit inside it. If it had formed second, its gravity would almost certainly have wrecked whatever formed before it. So when you study Jupiter's interior, you are not really studying a planet. You are studying the first step, the one that happened right after the star switched on, and the specific thing Juno was sent to find was a core. Here is what we believed before Juno arrived, and it is worth being precise about it, because the precision is the whole story. There were 2 competing ideas about how a planet like Jupiter gets built. The first one is the conventional accretion theory. In this version, you start with solid material rock and ice clumping together in the disk of debris left over around a young star. Once that clump reaches a certain threshold, roughly 10 times the mass of the Earth, its gravity becomes strong enough to start pulling in hydrogen gas. And once that begins, it does not stop. The gas piles on, compresses under its own weight, and the planet inflates outward from a dense seed. Under this theory, there must be a compact core of heavy elements sitting at the center of Jupiter right now. The second idea is older and stranger. It was first proposed in 1951 by the Dutch-American astronomer Gerard Kuiper, and it is called gravitational disk instability. In this version, Jupiter never had a seed at all. A large clump of gas and dust in the early solar system simply collapsed in on itself and contracted into a sphere not unlike the way the Sun did, only smaller. Under this theory, there is no core, there is just gas, all the way down. Both were reasonable, both had supporters. And for decades, the argument could not be settled, because you cannot open a planet. So Juno spent 8 years measuring gravity. Every time the spacecraft dropped in toward the planet, the radio link back to Earth was tracked with extraordinary precision, measuring the tiny shifts in frequency caused by Juno speeding up and slowing down as the mass beneath it changed. Add up enough of those passes and you can map the gravitational field. Map the gravitational field and you can read the subtle irregularities in how the planet spins. Read the spin, and you are doing the egg experiment. It took 45 of those passes to build the model. The closest of them brought Juno down to 138 kilometers above the reference surface of Jupiter. Now, here is what they found. There is no compact core. Or, if there is one, it is so small that Juno cannot confirm it exists. Let that sit for a second, because it is the single most consequential sentence in this entire mission. The team can place an upper limit on a compact core of heavy elements at somewhere around 5 to 6 Earth masses, and the whole planet is 300 Earth masses. Which means the seed that the entire accretion theory depends on, the thing that was supposed to be 10 Earth masses before it could even begin collecting gas, either shrank or scattered, or was never there. But the second finding is the one nobody was ready for. Juno did not find gas all the way down either. It found something in between, something with no name in the older models, because none of the older models had a slot for it. They call it a dilute core. The word dilute is doing a lot of work there, so let's be careful with it. A dilute core is not a solid object. It is not a ball. It is a region extending outward from the center, reaching roughly halfway to the surface of the planet, where heavy elements are mixed in among the hydrogen and helium at a higher concentration than anywhere else, but without ever forming a boundary. There is no line, there is no shell, there is no point where you could say the core stops and the planet begins. Bolton describes it as diffuse. As you travel inward, the density simply increases and increases and keeps increasing. It is much denser than the outer envelope. It is much less dense than the compact core that people expected to find. And the edge of it is fuzzy in every direction. And the crucial detail, the one that turns this from a result into a genuine problem, is that nobody predicted it. Bolton has been direct about this. Before Juno, nobody had theoretically considered it as a possibility. The options on the table were a small compact core, or none at all. A third option was not being ignored. It had not been imagined. Now, getting from raw gravity measurements to that conclusion is where the story takes a turn that nobody planned for either. To model a planet's interior, you cannot treat it as one thing. You have to treat it as a stack. The technique has been around for over a decade, and it is called concentric Maclaurin spheroids, which sounds forbidding. But the idea is simple enough that Caspi reaches for the kitchen again to explain it. You model Jupiter as an onion, many thin layers nested inside each other, each one with slightly different physics governing it. Near the surface, you have an atmosphere. Below that, an envelope. Deeper still, plasma. Deeper again, something hot and dense, and possibly close to solid. Before Juno, you could get away with a handful of layers, because the data was not good enough to notice the difference. That is not true anymore. Juno's measurements across 83 orbits, gravity, temperature, and a great deal else are so precise that matching them requires an onion with a very large number of layers. And each layer you add multiplies the number of possible configurations. The number the team ended up staring at was billions. Billions of possible interior structures, every one of them consistent with a planet of Jupiter's size, shape, and mass. Calculating them all with the traditional method would have taken longer than anyone has. So they built something new. A neural network trained on the physics of the older model. They call it a neural version of the same technique, which does not need to solve the equations from scratch for every candidate planet, because it has already learned how they behave. Feed in the Juno data. Get back the structures that survive. The speed-up was a factor of 100,000. Work that would have taken 100,000 hours now takes 1. Billions of possible Jupiters collapsed down to 4. And then, by folding in physical assumptions and data from earlier missions, the 4 collapsed to 1. That one structure says the compact core is either non-existent or very, very small. It says the dilute core does not extend beyond half the planet's radius. And it says the envelope wrapped around all of it is relatively cold and relatively light, which follows necessarily, because the total has to add up to the mass we already know. Caspi has pointed out something that is easy to miss here. When Juno arrived at Jupiter in 2016, this kind of machine learning was in its infancy. The spacecraft was already in orbit, already returning data, before the tool that would eventually interpret that data existed in any usable form. He describes it now as a new member of the team. Bolton adds the caution, and it is worth repeating exactly. They are using it, but it is not finished. There is no published paper yet. There is no consensus yet. This is a result moving through the scientific process, not a result that has come out the other side. So what is actually down there, physically? Working inward, the visible cloud tops, the belts and zones and the turbulence along their edges where winds running in opposite directions grind against each other. Below that, an atmosphere that the microwave radiometer has shown is not well mixed, meaning the neat, uniform picture we used to draw is wrong. Deeper, the pressure builds until, at a depth of around 7,000 kilometers, the hydrogen and helium become so dense and so ionized that they turn metallic. Below that, the layers of the dilute core growing heavier with every kilometer, with no boundary anywhere. And somewhere at the very center, possibly something small and compact, or possibly nothing at all. One more detail before we move on, and I want to plant it here rather than explain it. When the navigation teams model Juno's motion during those close passes, the equations do not quite close. There is a small residual force acting on the spacecraft near its closest approach that no model accounts for. To make the numbers fit, analysts insert what they call an empirical acceleration, essentially a placeholder for a push whose source is unknown. When you study the direction of that push, it changes rapidly, flipping sign within minutes, following no pattern before or after the pass, which means it cannot be traced back to anything identifiable. Something is nudging the spacecraft. Nobody can say what. Now we get to the part of the mission that does not resolve. Start with the magnetic field, because it is the strangest. Jupiter's magnetic field is not a tidy dipole like Earth's. Juno's mapping revealed enormous asymmetries between the hemispheres, including a band of intense flux in the north, and near the equator, an isolated, concentrated patch of magnetic field that the team nicknamed the Great Blue Spot. Here is what makes it remarkable. When you compare the newer magnetic model against the earlier one built from Juno's first years, almost nothing has changed across the planet. Almost. The one place where measurable change over time shows up is at the edges of the Great Blue Spot, and the shape of that change matches the winds. South of the spot, where the zonal winds run west, the magnetic field is being dragged west. North of it, where the winds run east, the field is being stretched east, which means the weather is deforming the magnetism. On a planet where the field is generated thousands of kilometers below the weather, that is not a small observation. It is direct evidence that the winds at cloud level are not a surface phenomenon. They extend down far enough to grab hold of the machinery underneath. And the gravity data says the same thing independently. There are significant gravity anomalies at around 23 degrees north and 15 degrees north, in exactly the latitudes where the wind speeds peak, implying density structures thousands of kilometers beneath the visible surface. Then there is the ionosphere, which is where this gets genuinely eerie. Ground-based observations of Jupiter's upper atmosphere, averaged over dozens of nights in the late 1990s, produced a map of infrared brightness across the whole planet. That map is covered in features: dark patches, bright patches, a long sinusoidal band of dimness running around the entire planet, offset from the equator. For years, nobody could explain them. But when researchers laid that old brightness map over Juno's magnetic field models, the features started snapping into place. The dark ribbon sits precisely along the magnetic equator, where the field lines run parallel to the surface within 5 degrees of it. Every single measurement comes in below the median brightness. Another dark region sits directly opposite the Great Blue Spot, magnetically connected to it. A cold spot that has held its position for at least 15 years turns out to sit where the field lines run nearly vertical. The pattern is bimodal. The ionosphere goes dark where the field is flat, and it goes dark where the field is steep, and in between, it behaves normally. Not all of them fit. One feature in the northern hemisphere, a broad anomaly, larger than the others, does not align with anything. The researchers list it alongside the rest and describe it, in the published summary, as remaining unexplained. And then there is the composition problem, which is the one that keeps Bolton up. Juno measured the abundance of heavy elements in Jupiter's atmosphere: carbon, nitrogen, sulfur, everything past helium. Compared to the Sun, the atmosphere is enriched by a factor of 3 or 4. That is a solid measurement. But the gravity data implies the deep interior is not enriched in the same way. So you have a planet whose outer layers are richer in heavy elements than its inside, and Bolton's own assessment of that is worth quoting almost exactly. He does not have an answer for how something like that could happen, or even how it could evolve into that state. It might mean there is something about the data we still do not understand. It might mean the deep interior is warmer than the models assume. Nobody knows how to build a Jupiter like this. So, is Jupiter strange, or is this simply what giant planets are? That question is not rhetorical, and the answer matters more than the individual findings do, so it is worth walking through the reference points we have. Start with what Jupiter almost was. The planet is so overwhelmingly composed of hydrogen and helium that if it were 13 times larger, the pressure at its center would begin burning deuterium. At that point, it would stop being a planet in any meaningful sense and start resembling a failed star. Jupiter is not the biggest planet in some open-ended ranking. It is close to the ceiling. Now look sideways, at Saturn. The data we have suggests Saturn may also have a dilute core, which would mean the thing Juno discovered, the structure nobody predicted, might not be a Jupiter quirk at all. It might be the normal condition of giant planets throughout the cosmos. And that possibility, rather than settling anything, opens a much larger question, because it means our formation models are not wrong about one planet. They are wrong about a category. Then look at the moons. Because Juno turned that same microwave radiometer on them, and this is where the mission produced its most unexpected result. Io is the most volcanically active world in the solar system. It orbits Jupiter every 42.5 hours on a slightly stretched path, which means the distance between them varies by around 3,500 kilometers over the course of a single orbit. Jupiter's gravity squeezes and releases it over and over forever. The internal heat that generates is enormous, a total power output on the order of 100 trillion watts. For decades, the obvious conclusion was that all that heating had melted the inside of Io into a global ocean of magma sitting just below the crust. It was the natural explanation for the volcanism. Magnetic measurements from an earlier mission seemed to support it. Juno flew past Io twice, at the end of 2023 and the start of 2024, at an altitude of about 1,500 kilometers, and measured how much the moon deforms under Jupiter's pull. If there were a shallow ocean of liquid rock under the crust would be mechanically decoupled from everything below it, and Io would flex dramatically. It does not. The measured deformation is small. There is no shallow global magma ocean inside Io. If any magma ocean exists at all, it has to sit deeper than about 318 kilometers down, far too deep, to be the source of what erupts at the surface. The volcanoes are not being fed by an ocean. They are being fed by melt migrating upward through a mostly solid mantle, fast enough that it never has time to pool, and that finding travels a long way. The early moon almost certainly did have a shallow magma ocean, formed by the giant impact that created it. Io, which is heated continuously and violently and has been for billions of years, does not, which means intense tidal heating does not guarantee a magma ocean, a conclusion that reaches straight out to the exoplanets, where that assumption has been quietly load-bearing for years. The same instrument found something else at Io. Looking a few meters down into the crust, everywhere Juno pointed, the temperature rose by more than 40 degrees Fahrenheit within just a few feet of the surface. That gradient is far too steep for sunlight to explain. It is heat coming out from underneath. Across the whole moon, the energy release runs up to 30 times Earth's average, though locally, per square meter, it is gentle enough that Shannon Brown at the Jet Propulsion Laboratory compared it to a small nightlight glowing under every square yard of ground. And the surface itself turned out to be almost nothing like the pictures suggest. Away from Io's mountains, and there are more than 100 of them, some reaching 17 kilometers high, the moon is smooth, broad flat expanses running 100 kilometers or more. Brown's comparison was the Great Plains of North America, and the material covering them is not solid rock. Its density is closer to pumice, or to fluffy volcanic ash. At Europa, the same instrument measured the ice shell and found it to be about 30 kilometers thick, threaded with tiny pores and cracks a couple of 100 meters down, and surprisingly, remarkably consistent. The thickness barely varies. What varies is the imperfections inside it. There is one more region, and it is the one almost nobody knew existed. Jupiter has rings. They are not like Saturn's. Saturn's rings are bright because they are made of water ice, and ice reflects sunlight. Jupiter's rings are made of dust thrown off its smallest inner moons by meteoroid impacts, and dust does not shine. They are so dim that most people have never heard of them, and the region they occupy is laced with radiation belts violent enough that very few spacecraft have ever gone there. Juno's orbit has been slowly drifting into it, not by design. Jupiter is not a perfect sphere, and its oblateness has been torquing the spacecraft's orbit around for a decade, walking the point of closest approach up from near the equator toward the North Pole. The mission is now exploring a region it was never sent to. To photograph something that dim, the team uses a camera that was never intended to take pictures of anything. The Stellar Reference Unit is the spacecraft's star tracker, a navigation instrument built to be sensitive to extremely faint light. Heidi Becker at the Jet Propulsion Laboratory has been clear that using it for science was never planned. It was born out of curiosity. Very late, when somebody wondered whether an instrument that sensitive might be able to see the dust. The very first image it ever took was of the ring, and it remains the only image ever collected from inside a ring system, looking outward. Then there is the dust that hits the spacecraft. When a grain strikes Juno, it knocks microscopic fragments of the spacecraft loose. Those fragments drift across the field of view of the cameras and catch the sunlight, and in the images, they look like fireworks. The technique was not invented at Jupiter. It was worked out during the cruise, when a star camera team noticed the stars were not moving the way they had predicted and realized dust was the reason. On the way out, They used it to map the interplanetary dust and even flew through the tail of a comet. And Juno can hear the impacts as well as see them. Each strike generates a small cloud of charged particles around the spacecraft, which registers on the plasma waves instrument as an electrical pulse. That instrument records amplitude against frequency, which is the same thing sound is. So the data can be shifted directly into the range of human hearing, roughly 20 to 20,000 cycles per second, and played back. The problem is that the pops are buried in what sounds like noise, which is where the machine learning comes back in, sorting an enormous dataset into two piles. This is dust, and this is something else. And at the outer edge of the faintest ring sits a small moon named Thebe. Juno passed within about 5,000 kilometers of it and returned a single image at roughly 3-kilometer resolution. It is the only one they will get, because the star camera cannot take pictures quickly enough for a second attempt. The last spacecraft to get anything close was Galileo, around the year 2000s, from a couple of 100,000 kilometers away. Thebe is about 100 kilometers across. In the image, there is one enormous crater, possibly around 40 kilometers wide, nearly half the width of the moon itself. Bolton, presenting it in Vienna, said the obvious thing out loud: "This is Jupiter's own Death Star." The left side of the moon in that image is lit by the sun. The right side is lit by Jupiter's sunlight scattered off the planet and back onto the moon, so faint that only a camera built to see stars could register it. And Thebe may be the reason the outer ring exists. It sits at what Bolton calls a magic point, close enough to Jupiter that its own gravity and the centrifugal force of its orbit nearly cancel out. Dust on its surface barely needs any push at all to leave. So it does, continuously. And it spreads out behind the moon into the ring we can barely see. Juno's nominal mission was 32 orbits. As of that briefing in Vienna, it had completed 83. The spacecraft is healthy. The instruments are working. It is currently funded. And when the team was asked how much longer it might last, nobody would offer a number. But the data it has already returned has done something odd to the field. It has not filled in the picture. It has taken a picture that everyone agreed on and removed the parts that were holding it together. We came looking for a core and found a structure that has no edge. We built two theories of planet formation, spent 70 years arguing between them, and got back a planet that fits neither. We measured an atmosphere richer than the interior it sits on, and we cannot say how a planet does that. We assumed extreme heating creates oceans of magma, and Io, the most violently heated world we know of, quietly declined. Something is still tugging on the spacecraft at closest approach, changing direction every few minutes, and we do not know what it is. There is a feature in Jupiter's upper atmosphere, dark and enormous, and the honest scientific summary is that it remains unexplained. Stephen Levin, the project scientist at the Jet Propulsion Laboratory, put it in a way that stays with you. As humans, he said, we have a tendency to fill in our ignorance with simple models, but the details are always more complicated. That is what the eggs were about, back in that room in Vienna. Not the trick, the lesson underneath it. You can hold something in your hand, know its weight exactly, know its shape exactly, and still be completely wrong about what is inside right up until the moment you find some way to make it move. We spent 8 years making Jupiter move. We measured its gravity to a precision no one had ever reached. We taught a machine to imagine billions of versions of a planet and throw almost all of them away. And what came back was not the answer. What came back was the discovery that the largest, closest, brightest, most studied object in the sky beyond the sun has been sitting there the whole time, with a structure we did not have a word for, and that Saturn may have one too, and that the giant planets circling other stars probably do as well. We looked at the first thing that ever formed around our sun, and it turned out we had never really seen it at all.